Chapter 6 is about humidity, saturation, and atmospheric stability. Our driving question is, how does the cycling of water in the Earth atmosphere system help maintain a habitable planet? The chapter opens with an interesting case in point about atmospheric rivers. These are bands of concentrated water vapor transport in the lower atmosphere. They've been studied extensively off of the U.S. western coast, and it's been found that they play a very important role in providing fresh water to the western U.S. 30 to 50% of the average annual precipitation for the West Coast comes from these atmospheric rivers. So this is a river in the atmosphere, not in the ocean, of water vapor that's transported. The global water cycle is a way to account for all of the water in the Earth atmosphere system, which is a constant. There are tiny amounts that can come in through meteorites, but it's negligible. There are tiny amounts that can be lost through other processes, but we are ignoring those here and saying that the amount of water is, for all intents and purposes, constant. Most of the water is stored in reservoirs, the ocean being the main one. The ocean holds 97.2% of the water on Earth. The other biggie are ice sheets and glaciers, which make up 2.15% of the water in the global water cycle. The sun is what's responsible for the global water cycle, because without the sun we wouldn't have any evaporation. And then gravity is what prevents the water from escaping to space. It keeps it here on Earth. So where's the water stored? Here's a breakdown. You can see most of it is stored in the ocean and glaciers, and then smaller amounts are stored in groundwater, freshwater lakes, and so on. And you see here that the atmosphere, the subject of this whole course, makes up a very tiny percentage of the total water of the Earth atmosphere system, but it's vital to our weather and also to distributing water to different parts of the planet. This schematic shows the global water cycle, and we start with the open water. So we have the open ocean and open water on the Earth, on the land, and the water evaporates because of the sun, heats up, some of that water evaporates, and as it rises up into the atmosphere as water vapor, it condenses. As we'll see later in this chapter, it condenses to form clouds, and once the clouds grow to a specific height, then we can see some precipitation form. So the precipitation delivers the water back to the oceans and back to the land. Over here on the land side, we see that it's not just open water sources that evaporate, it's also vegetation that transpires. This process is called transpiration. And we also have snow and ice that can go directly from a frozen state of water to a vapor form of water through a process called sublimation. So it bypasses the in-between step of being a liquid and goes directly to a gas. When the water falls back to the earth as rain, infiltrates through the soil into what we're just calling here groundwater storage, and some of that eventually makes its way back out into the ocean. This graph shows a satellite composite image, water vapor for the world. And you can see the water vapor is in constant motion. So this is vapor form of water in the atmosphere and how it's being transported around the globe. The processes responsible for global water transfer include the phase changes of water, which we talked about previously: evaporation, condensation, and transpiration. When we combine evaporation and transpiration, we use a word called evapotranspiration. It's just the total amount of water that is transferred from liquid to vapor by evaporation and also by transpiration. Sublimation is the process of ice or snow, so water in its ice or snow, its frozen state, becoming vapor without first becoming liquid. And deposition is the opposite, water vapor that becomes frozen without first becoming liquid. Another process for transferring the water is precipitation in all of its forms: rain, snow, etc. Humidity describes the amount of water vapor that's in the air. And humidity is tricky because it varies annually, daily, from within one day as well as from day to day, and it also varies geographically. For those of you that have lived in or visited eastern or midwestern states of the United States, you know it's very humid there compared to how it is here in Arizona, which, as everyone says, has a dry heat because there's not much humidity in the air. Humidity is measured in a number of ways. Through vapor pressure, which is the component of atmospheric pressure due to water vapor, so how much pressure is exerted by water vapor in the atmosphere. Mixing ratio, which is the mass of water vapor per mass of the remaining dry air. Specific humidity is the mass of water vapor per mass of the air containing the vapor. These are very similar, mixing ratio and specific humidity, so they're usually considered to be about the same. And absolute humidity, which is the mass of the water vapor per unit volume of humid air. When we talk about humidity in the atmosphere, saturation is an important concept. Saturation is the state when the air is holding the maximum amount of water vapor that it can hold. So there's a dynamic equilibrium that occurs when liquid water becomes vapor at the same rate that vapor becomes liquid. So that's another way of saying saturation. So we can add the word saturation to these different measures of humidity, like saturation vapor pressure, saturation mixing ratio, and so on. Now, it's complicated to talk about saturation and humidity in the atmosphere because there's so many variables that change. For example, if you change the air temperature, it will disturb this equilibrium. It will change the saturation. So for example, if you heat water, it increases the molecular activity and therefore the kinetic energy, and molecules more readily escape the water surface as vapor. So changing air temperature can change saturation. In these graphs, we see the relationship between temperature across the x-axis and saturation vapor pressure in millibars across the y-axis. And you can see that as the air gets warmer, the saturation vapor pressure increases. And that is because warm air can hold more water vapor than cold air. So if the air is warmer, it has the potential to hold more water vapor than cold air does, and therefore there's more water vapor there, and the vapor pressure increases. And you see in both of these graphs here that they do a little blow up here for temperatures below zero, where we have ice instead of vapor pressure. You see the slight difference between liquid and ice happening, the slight difference between liquid and ice compared to water vapor. So this first graph shows variation in saturation vapor pressure, and then the second one shows the same thing but for saturation mixing ratio. So same tendency. Again, the point here is that warm air can hold more water vapor than cold air. Relative humidity is a more common term. It compares the amount of water vapor that's actually present in the air relative to the amount of water vapor that the air could hold if it were saturated. So it's a measure of the actual amount of water vapor compared to how much water vapor the air could hold. Relative humidity is given as a percentage, so you see here a couple of different ways to calculate it depending on if you're dealing with vapor pressure or mixing ratio. So here we have relative humidity equals the vapor pressure divided by the saturation vapor pressure, and then to turn it into a percentage, multiply it by 100. Same thing for mixing ratio. If you were able to hold temperature and pressure constant, then relative humidity would just vary directly with vapor pressure or mixing ratio. In other words, the more vapor that's in the air, the higher the relative humidity would be. However, it's not possible to hold temperature and pressure constant in the atmosphere. So if the amount of water vapor in the air remains constant, then relative humidity varies inversely with temperature. Let's look at it on a graph. So this graph shows temperature in red, and you can see the temperature scale over here on the y-axis on the left. This is time throughout a day. And then in blue we have relative humidity as a percentage. And this is the main relationship in this graph. So as temperature decreases, relative humidity increases. And then as temperature increases, relative humidity decreases. So temperature and relative humidity are inversely proportional. And again, remember, warm air can hold more vapor, more moisture than cold air. So as the temperature goes down, the air is not able to hold as much moisture. So the saturation point decreases, which drives the relative humidity percentage up. Right? Compared to when the temperature is hot, it's able to hold more moisture, so the saturation point increases, and that drives the relative humidity down. Down here in green, we have the dew point temperature. As we'll see in just a moment, the dew point temperature is the temperature to which the air must be cooled in order for water vapor to condense out as a liquid. So that's the dew point temperature, and you can see how it varies down below here. We'll talk more about it now. So dew point, again, it's the temperature to which air must cool in order to reach saturation. So once saturation has occurred, you have 100% relative humidity. The air is as humid as it possibly can be. So at saturation point, water vapor begins to condense out of the atmosphere. So as the concentration of water vapor increases, the dew point also increases. So if you add more water vapor, everything held constant except you add more water vapor, the dew point is going to increase. With high relative humidity, the dew point is closer to the current temperature than with low relative humidity. So if you pay attention when you're checking weather observations, try to notice the dew point temperature. In Arizona, it's always going to be very low, much lower than the air temperature, because we have very low humidity in Arizona. But when the humidity increases, the dew point temperature is going to become closer to the actual air temperature than when we have lower relative humidity. So dew are just small drops of water that form on surfaces, and any surface will serve as a surface that water can condense onto. So in the mornings, in moist environments especially, and sometimes here in Arizona, if the temperature has dropped at night to the dew point temperature, then we have dew that forms on the grasses and the different vegetation, as well as our cars and other surfaces. An example of this is if you have a cold drink, let's say a glass of ice water on a hot day. When you go outside, that glass cools the temperature of the air immediately around it, and it cools that air down to the dew point temperature of the air, which means that water vapor that's in the air surrounding your glass will condense onto your glass, onto that surface, and you end up with a sweaty glass. It's not really sweating, obviously it's not leaking from the inside. That moisture is coming from the outside, from the atmosphere, through this process of dew point temperature. If the dew point temperature is below freezing, then instead of dew, you'll have frost form on the colder surfaces. So this happens in the winter when you wake up and you have frost on your windshield. Again, the dew point temperature was reached in the night, but the temperature was below freezing, and so the condensation occurred as frost. These two graphs show seasonal humidity in the United States. On the left, we have the July average surface dew point temperatures. You can see that the dew point temperatures are much warmer in the eastern United States than they are for the west. Again, remember, the moister the air, the closer the dew point temperature will be to the actual air temperature. So here we can see that the west is drier than the east. And then for January, when things have cooled down, we see a more consistent profile across the United States. Precipitable water is the depth of water if all of the water vapor in a vertical column of air was condensed into liquid. So if you could take a column of air and get all of the water in whatever form it's in water vapor, whatever form it's in, and turn it into water, the depth of that water is what we call precipitable water. So the total precipitable water for the whole atmosphere is 2.5 centimeters or 1 inch. That's for the whole world. So if you could take all of the water vapor of the atmosphere and bring it down to Earth as water, it would cover the whole Earth in 1 inch of water. There's more water vapor in the tropics, so we have higher amounts of precipitable water there. These two graphs show that. So here we have the precipitable water in the summer months, and you can see higher amounts in the tropical areas reaching up into the United States, and then precipitable water in the winter months. We measure humidity through instruments called hygrometers. And hygrometers come in a couple of different types. There's a dew point hygrometer, which is kind of a fancy instrument that uses a temperature-controlled mirror and an infrared beam. And when the mirror reaches the point where condensation forms, it in fact causes that mirror to have water condense onto it, and that changes the beam of light that's sent out through the infrared beam, so that a sensor can determine that condensation has occurred and tell us the dew point temperature. Believe it or not, humidity is also measured through hair, through human hair, a hair hygrometer. Hair, as many of us know, I'm a woman with long hair who grew up in Indiana, so I know well that humidity makes your hair really funky. It makes it full of moisture. It makes it kind of fatter and longer as relative humidity increases. So a hair hygrometer takes human hair and a way to measure the amount of humidity in the air based on how that hair behaves. A hygrograph is a device that measures humidity over time. So like we saw with the barograph and the thermograph, there's also a hygrograph that you can see the trend of humidity over time. And then an electronic hygrometer, like the one you see in the picture below here, is based on resistance of certain chemicals if they absorb or release water vapor into the air. So it's a chemical process. So here we have temperature dew point sensor, a hygrothermometer. It's doing both. It's measuring the air and the dew point temperature. Finally, the Sling psychrometer is kind of popular in meteorology classrooms. It looks like this one, or they have lots of different looks, but basically you have two thermometers. And one of the thermometers has a little wick on it, a little sock, like a cotton sock. And you get that sock wet with distilled water, and then the handle allows you to spin this thing around. And as you spin it, the water that's on the sock evaporates and causes the temperature of that thermometer to decrease because of the latent heat that it takes to evaporate that water. So the temperature of one thermometer goes down while the other one is just reading the regular air temperature. And then once you get those two values, the wet bulb temperature, as the one with the sock is called, and the dry bulb temperature, there's a chart that allows you to compare the two, and it will tell you the relative humidity. Here we see water vapor in infrared imagery, satellite imagery. So we can attune our sensors that's on a satellite to read through the infrared spectrum that picks up water vapor. And that's what we see in these images. So the water vapor imagery shows water higher in the atmosphere as bright white, like we see here with Hurricane Irene. And water vapor that's lower in the atmosphere becomes grayer. And if there's no water vapor at all, then we're seeing just dark spots. So you can see here an image from August and an image from March 2009, typical kind of profiles for the US.